So now we've talked about functional programming and we've talked about object-oriented programming. I want us to compare functional and object-oriented programming now to understand when one or the other might be useful and how both of them play into the context of Python programming and programming in general. But first we need to talk about terminology because there is a massive lack of precision on the terminology of functional and object-oriented programming floating around in the programming community. And it's making all of these concepts harder to understand than they have to be. So I'm going to disambiguate some stuff now and graduate us from the terms that I've been using, functional and object-oriented, to more precise terms to describe exactly what we're talking about with the two different styles of programming. So I've referred to Python as a multi-paradigm language on one occasion, and you'll hear it referred to as a multi-paradigm language from other programmers as well. And that's not a lie. It is a multi-paradigm programming language. That having been said, let's talk about exactly what a paradigm is and then find out where Python fits in that spectrum. So, what is a paradigm? Well, let's talk about two different paradigms. That is, different ideas about how solving a programming problem can work. First is the imperative paradigm. Imperative describes a way of thinking about a programming problem. Specifically, thinking about a programming problem in terms of how to perform tasks and how to manage state. By contrast, declarative paradigm describes a way of thinking about a programming problem, specifically thinking about a programming problem in terms of what output we want without having to know the details of how we got there. So a paradigm describes a way of thinking about a programming problem, and we're talking about two, imperative and declarative. Different programming languages adopt each of these paradigms to different degrees. For example, in Ruby, when you want to write a web app, you inherit from classes, usually defined by a framework like Rails or Sinatra. Those classes are specially designed to help you keep track of state, like database records, attributes on objects, and behavior, which requests are supposed to route to what actions. By comparison, in SQL, you write a statement declaring what data you want out of the database and how you want it organized. SQL decides for you how to get the thing you want, whether to use indices, what order to do things in, etc., without bothering you to specify that information. In fact, when you write SQL, it is common for SQL to execute queries in a little bit different order than you define the query. So that's paradigm. We've talked about paradigms. Now let's talk about implementation. Chiefly, programming languages implement the imperative and declarative paradigms with object-based implementations and function-based implementations. So now we're talking about object-based and function-based. The implementation describes how we do something in code, as opposed to the paradigm, which describes how to solve a programming problem in general. So, an object-based implementation of a code solution depends on the instantiation of, use of, and inheritance from objects. Meanwhile, a function-based implementation of a solution in code depends on the definition of, use of, and passing of functions to functions. These are not the only ways to implement the paradigms. Here's a huge, common example. SQL is largely not a functional language. You aren't passing functions around to functions, but it does implement the declarative paradigm. Now, the way SQL works is a whole fascinating subject that I'm not talking about in this class because I'm supposed to teach you Python, but I think it's a fantastic example of where understanding multiple different languages makes you better at understanding each individual language. The point is, The paradigms, imperative and declarative, and the implementations, object-based, function-based, or otherwise, are not equivalent things. They are not the same thing. Okay, so we've talked about paradigms and we've talked about implementations. Now let's talk about another term, the term oriented. When a programming language is oriented in a certain direction, it means that the constructs available in that language loan themselves better to one implementation or the other. So, here we have two adjectives again. Object-oriented, which describes a programming language. Specifically, one whose constructs make object-based solutions convenient to implement. The other, functionally oriented, describes a programming language. Specifically, one whose constructs make function-based solutions convenient to implement. Now, it is possible, although kind of difficult, to make a language that only supports one type of solution. Haskell is pretty close to a functional language. Alloy is pretty close to an object language. However, the utility of a language drops off pretty fast if it only does one or the other, because both are at least a little useful in most programming areas. So, oriented means one is more convenient, but you can kind of do both. Now, colloquial terminology about programming language absolutely butchers this by referring to functionally oriented languages as functional and object languages as object-oriented, and languages that are oriented either way as dual paradigm, despite the fact that paradigm is an idea, not an implementation, and a programming language does not have a paradigm. I firmly believe that the reason that this functional versus object-oriented programming idea is so hard for people is that we use the same term to mean 6 different things, 2 of which are sometimes opposites. Now, I have a chart that I found to provide a visual, but it also butchered the terminology, so I fixed it. Here, we have a list of characteristics and how they work in an object-based approach versus a function-based approach. So first, we have the programmer focus. In an imperative context, the programmer is focused on how to perform tasks and how to track changes in state. In a declarative context, the programmer is focused on what information is desired and what transformations are required. Now, in an object-based approach, state changes are important, the order of execution is important, the primary control flow is through loops, conditionals, and method calls, and the primary manipulation unit is an instance of a structure or a class. Now, when we are writing a function-based solution, state changes are typically non-existent. The order of execution is of low importance. The primary flow of control is through function calls, including recursion, and the primary manipulation unit is a function as a first-class object and a data collection, such as a list. All right. So Python is an object-oriented language. Python is also a multi-paradigm or dual paradigm language. People will argue when I say Python is object-oriented that it is, in fact, dual paradigm. I disagree for reasons that you are now intimately familiar with, and I believe that the inclusion of oriented at the end, by definition, means that the language is to some degree dual paradigm. You can do functional programming in Python. However, Python is designed to prioritize object-based programming solutions. We'll come back to this. Let's take a look at different implementations in Python by example. First, we have an object-oriented approach. Here, I have a red-shouldered blackbird class, a big bird class, and a parrot class. Each of them have a respond method defined on them that prints a different message depending on the bird. When you make eye contact with any of these birds, their respond method is called. And what that means is you can use the same method with the same one-line call to the respond on any of these birds and get different results, as you can see. Now, one of the things that object-oriented programming is very good for is managing state within objects, and we see an example of that with our parrot. So our parrot doesn't always respond the same way when you make eye contact with it, whereas Big Bird always does and the red-shouldered blackbird always does. For the parrot, every time you make eye contact with him, he gets more annoyed. The annoyed level is a piece of state in the parrot object. And if that annoyed level gets high enough, then the parrot's response changes from "I'm going to bite you" to "Okay, that's it, bucko, you're getting the beak." Check it out. If we call this same method on this same parrot multiple times, we ultimately get an angry parrot. That is a demonstration of how object-oriented programming helps us to manage state. Now, if I were writing a program where I wanted to add new birds all the time, then an object-oriented approach might work well for me, because all I would have to do is write a new object with the respond method defined on it, and eye contact with would automatically work. Now let's look at similar code in a functional pattern. Here I have a new method, make eye contact with some bird. I have just one method, and I check the type of the bird, which is passed in. If the bird is equal to a parrot, I print, "I'm going to bite you." If the bird is a red-shouldered blackbird, I print, "I'm going to land on your head, scream at you, and then steal your French fry." And if the bird is a big bird, then I print, "I'm going to teach you a letter of the alphabet." I can call this function on any of these stringified bird types. Now, what if I wanted to add a bird in this situation? Well, I would have to add, for every make eye contact with or other function that I have that switches on bird, I would have to add a new case for every single bird to each of those functions. But if the rate of change in my program wasn't that birds were going to be added quickly, but rather that interactions with birds were going to be added quickly, or other bird-related behaviors were to be added quickly, then it would be faster and easier in a functional construct, because I could copy a function like that one, paste it somewhere else, and change out the behaviors for each of the individual types of bird. Whereas if this were object-oriented, rather than just adding one new function, I'd have to go back and add a new function to every single bird object. An object-oriented pattern makes it easier to add objects later. A functionally oriented pattern makes it easier to add more behaviors later. And which one you choose doesn't depend on the language. It doesn't even depend on the application. It depends on the specific problem that you are trying to solve at that time and how you expect that problem to change over time. How you expect that code to change to address that problem over time. That's the criterion that you can use to determine whether a part of a code base might make more sense in an object pattern or in a function pattern. In addition, imperative programming is often particularly useful for describing and directing the interactions between different concepts. We see this in many web frameworks. We have controllers that are responsible for orchestrating the behaviors of databases and model classes and view classes, and in that situation, an object-oriented paradigm works really well. or rather, an object-oriented implementation of the imperative paradigm works really well. Declarative programming, by contrast, is often particularly useful for manipulating collections of data where the datums are independent, not specifically interacting with one another. So if we want to run a transformation on every single row of a database, but those rows' transformations don't depend on each other, then in that situation, a functional implementation can make a lot of sense. And we see that a lot of pipelines that munge data end up using a functional approach for that reason. Let's talk about some more examples. So we discussed how web frameworks allow you to inherit from objects. Mobile frameworks often also have you inherit from objects. The superclasses can handle all these objects' instantiation and relationships with each other, while you happily add in what the pages should look like or which data the endpoint should fetch, etc. Golang, a functionally oriented language, by contrast, hasn't gotten as much traction as a language for writing APIs or web apps. And the tooling around doing so with Golang is about as mature as it is for Swift, an object-oriented language that is 7 years younger than Golang. Let's look at another example. SQL, a declarative language, is chiefly used for what? Fetching collections of data out of databases, the type of situation where we've discussed that a declarative paradigm is helpful. Functional approaches are also popular in extract, transform, load pipelines that take a bunch of data, do something to it, and then move it somewhere to a new file, for example. Functional approaches are also popular for transforming a bunch of data that was pulled from an API before displaying it. Once again, potentially a lot of data, all the little datums are independent of each other. So we can do some kind of batch job to transform them all. People tend to always get functional programming and functions that specifically manipulate lists mixed up. In fact, most Python resources do this. If you look up functional programming in Python, 95% of what you find is just how to use map and filter, the end. But the declarative paradigm and a function-based approach to implementing that paradigm is a much bigger concept than two functions that are implemented as Python built-ins. There is a whole philosophy behind when and how to use them. There are various approaches to how to implement them. And although those approaches are not particularly prioritized in the Python programming language, they are available. You can use them with map and filter, or you can use them without map and filter, because this whole concept is much bigger than map and filter itself. But I also want to talk about map and filter specifically in the Python programming language. Python is not built particularly well with regard to functional constructs. Here's why. First of all, if you want to end up using any of this for anything other than iterating through it, you have to convert the result of the map and filter functions in and out of list format. So, for example, when I run this filter, what I get back is a filter object. Sure, I can iterate through it, but I can't do any of the other things that I would expect to be able to do with a list or a set or a dictionary or even a string or another iterable collection. It's not particularly helpful. I have to do this conversion in order to be able to even see my data. Now, if I can't look at a filter object without making it a list, perhaps I could at least keep doing functional processing on it. Let's look at an example. So here, I have my evens thing, and it's a filter, right? Well, maybe I can pass that in, right, as a collection to map, and I can square everything in my filter. I ran the code, so it seems like that worked. What I'm expecting to see when I get done is a map that contains 2 squared, which is 4, then 16, which is 4 squared, and so on and so forth, right? So let's take a look at what squared evens is when we convert it to a list. It's an empty list. It's not what we expected at all, but it also didn't error out. This is the second problem with Python's functional constructs. When you don't convert everything in and out of a list for every operation, it doesn't throw an exception. Instead, it looks like it worked, except that it didn't, which is super unclear. What that means is that the functional methods in Python don't support a fluent interface. I can't chain my functional functions together. I have to save everything off as a variable, which I then have to either explicitly delete, like I'm writing code in the 70s and I'm in charge of my own memory management, or else take up multiple times as much memory as I need for the final thing that I'm actually asking for anyway. I have a list here, right? And then I have evens, which I filter the list based on something. I don't need listo anymore, but now it's memory, it's not deleted. But if I want to use evens for anything, I can't pass it directly to map. I have to save that off as a list too. I'm never going to reference evens as list again after I put it into my map. And then I have a map called squareds, but I can't do anything with a map object, so I have to convert my squareds map object into a list in order to be able to get my squared as list. All of these things, these four, I'm never going to use again. But they're all still in memory until I explicitly delete them. Needing to explicitly delete objects to free memory is something that I expect modern programming languages to take care of for me. And sure, none of these things takes up that much space, and sure, eventually garbage collection will take care of them. Python will ultimately trace through and get rid of things that I don't need. But they aren't going to be automatically deleted by reference counting because each of these four things still has references. It's still assigned to a name. If I want them gone, I have to manually manage my own memory. I have to delete the names, and I should not have to do that. But finally, I did get my squared as list collection. It's worth noting that I could avoid the extra memory load by a means that you may have already thought of, that is, assigning each step back to the same variable name it transformed, rather than using separate names up here. And that would work. But here's the thing. What that would mean is that at every step, I have a name that might not actually represent what's happening. Here I've got a list, and I've named it listo. So I reassign my filter object to listo. Now I have a thing named listo that's literally not a list. Then I turn it back into a list, but it's unclear how that listo differs from the pre-transformed value that we have up here. Then I map over it. Once again, not a list, named listo. That's unclear. Finally, I convert my thing named listo to a list and assign it back to listo. Sure, this would save me a little bit of memory, but good luck to any programmer who's trying to figure out what I'm doing here. The whole point of Python's design is to be explicit. And this is less explicit about what's going on because a misleading name is worse than no name at all. The conclusion here is that functional programming isn't bad, but Python is kinda bad at it. Now, I want to introduce a question to you. That is, what is a fluent interface and how does it solve this problem? I'm not going to answer that question now. Instead, you're going to implement one in your homework to find out. You can see that here, that in your homework problems, we are going to implement a fluent interface, similar to one that you would find in Java. One other thing I also wanted to note as a bonus was that we do have some options if we need the strengths of both object-based and function-based programming in some area of code. Maybe we're going to be adding objects and we're going to be adding behaviors. And so we need a solution that makes it easy for us to add both of those things in both directions. The visitor pattern is sort of a way to get this. So it's out of scope for this video, but I found a tutorial that I think explains it really well, linked at the bottom of the notebook, if you're interested. Programming language designers will frequently use the visitor pattern to add behaviors to each of the types that are defined in the programming language.